Hello everyone, welcome back. So in today's video, we'll take up a problem that appeared in a recent Russian Olympiad. So this problem is mainly based on, you could say, Newton's laws of motion and a little bit of electrostatics. So we have an inextensible weightless thread whose length is L, and it is charged uniformly along its length with a positive charge of linear density lambda. Okay, so this thread that you see in the diagram, it's uniformly charged, and its linear charge density is given to be lambda, and its length is given to be L, and it is an inextensible string. Also, it doesn't have any mass. Okay, one end of the thread is fixed, so this is the end that is fixed, and a small load of mass m is attached to the other end. Okay, so the mass m is attached at this particular end, and the system is given to be placed in a uniform electrostatic field. Okay, so as you can see, there is some electric field which is uniform, and it is in some arbitrary direction like this, and it's given that the system is positioned in such a way that the tangents to the thread at the point of attachment and at the location of the load are horizontal and vertical. So what they're trying to say is the point where the thread is fixed, if you draw a tangent to the thread at this location, it is actually horizontal, and similarly if you draw a tangent to the thread at this location, it is actually vertical. Okay, so now the question is, the load is located at a distance capital H below and at a distance s to the right of the point of attachment. Okay, so this length is s and this height is h, and now the proper electrostatic field of the thread charges can be neglected. Okay, so the contribution to the field by the charges present on the thread, that we can consider it to be negligible. So we only have to consider this uniform electric field when it comes to force calculations. Okay, and the acceleration due to gravity is g, and it is vertically downwards. So so finally the question is that we have to determine what is the magnitude of this field E. So pause the video guys and give this problem a try. Okay, and then check out the solution. Okay, so this is the diagram of the situation guys. The electric field, it was given to be in some arbitrary direction, right? Okay, so first let's define two directions. So I'm going to consider the position where the mass is present as my origin, and I'm going to consider this direction, which is in the vertical direction, as my y-axis, and I'm going to consider this direction as my x-axis. So now I'm going to break E vector as Ex and Ey. Okay, so now the reason I broke it down is because if you take an infinitesimally small element on the thread, we can treat it like a point charge, right? And the point charge will feel a force in the x direction and in the y direction, right? And the y direction force is just going to be dq multiplied by Ey, and the x direction force is just going to be dq multiplied by Ex. Okay, and you can basically say the same thing for all the elements present on the thread. So if you want to write the net electric force acting on the thread in the x direction, it's just going to be the total charge multiplied by Ex, and the net vertical electric force is going to be the total charge multiplied by Ey. So that's the benefit of writing it as Ex and Ey. So now let's remove the small element. Okay, so the first equation is, I can write the net electric force in the y direction as Ey multiplied by the total charge. So the linear charge density is lambda and the total length is L, so the total charge is going to be lambda into L. Okay, so now what are the other forces in the y direction? So I'm going to take the string plus the mass as my system. The other force in the y direction is the weight of the particle, which is mg, and then we have a tension force acting at the fixed end, but the thing is, this tension force is in the x direction, right? So first let's write down the force balance in the y direction. So this is just going to be the electric force in the y direction, which is lambda L Ey. This would be equal to mg. Okay, so this is my first equation. Okay, now let's write down the force balance in the x direction. So in the x direction we have the tension T acting horizontally, and we have Fe, the electric force in the x direction. So the tension T is equal to lambda L multiplied by Ex. Okay, and this would be my second equation. So I mean, if you observe from the first equation, we can directly get Ey in terms of the known variables, but T is an unknown here, so we can't find Ex right now. So we have two equations and we have three variables. Our variables are T, Ex and Ey. So we need one more equation to get the answer. So for that, I'm going to take the system and just rotate it, right? Just so that the diagram looks neat. So this was my x direction and this was my y direction. Okay, and there is a force of mg in the horizontal direction. Okay, and of course the thread is tangent to the horizontal at the origin. Okay, so let's make the curve a bit short for some clarity. the x component of the electric field was in the minus x direction and we took it as Ex, and the y component was along the plus y direction and we called it as Ey. Okay, so now what I'm going to do is I'm going to take a small element on the rope somewhere over here. So let's draw a normal to one end of the element, and let's say it makes an angle theta. Okay, and let's connect the other end, and I'm going to say this small angle is d theta. Okay, and this line over here is the normal to the element. Okay, and the element is actually a tangent to the curve. Okay, so now the normal to our point makes an angle theta with the vertical, right? Which means if I draw a tangent to this point, it will make an angle theta with the horizontal. Okay, and let's say this is a zoomed picture of our element. So let's say the tension at this end, it will be along the tangent to the rope at that point. Let's say the tension at this point is T plus dt, and the tension at this point, it will be along this tangent. Let's say it is equal to T. So now let's draw normals to these 2 points. Okay, and they intersect somewhere over here. Okay, now the thing is, this angle over here, guys, it is equal to d theta, right? Now if I bisect this angle, then this angle is going to be d theta by 2, and similarly even this angle is going to be d theta by 2. Okay, now guys, this element, if you guys remember, it's a very tiny element. It's an infinitesimally small element. So this line that we just drew, it represents the normal to our element. Okay, so this line over here represents the tangent. Okay, so which means this line is the tangent to our dl element. So if you want to name this direction something, we can name this direction as the tangential direction and this direction as the normal direction. Okay, so now we are going to break down the tension forces along the tangential direction. Now guys, if this angle is d theta by 2, then even this angle will be d theta by 2, right? This angle is going to be d theta over 2. Okay, and similarly, if I draw a line parallel to T cap on the other end of the rope, even this angle is going to be d theta by 2. Okay, so we are done with marking the tension forces. Now we have to mark the electric field. Force due to the electric field. So let's mark that real quick. So Ex, if you observe, is in the downward direction. So on this dl element over here, it will be in the downward direction. And the magnitude is going to be lambda dl, which is the charge on this element, multiplied by the electric field Ex. And similarly, Ey will act in the rightward direction, and its magnitude is going to be lambda dl multiplied by Ey. Okay, so now we have completed the FBD of a dl element that is at a particular angle theta with the x-axis. Okay, so now what we're going to do is we're going to study the net force in the tangential direction. So let's try to write it down. So because of this t plus dt, there will be a t plus dt cos of d theta by 2, right? Cos of an infinitesimally small angle is to be taken as 1. So we're just going to take the tangential component along t cap as t plus dt itself, and similarly the component due to this tension force is going to be t. So the t cancels out the d, and what we are left is dt. Okay, and this dt will be equal to the net component of the electric field in the minus t cap direction. Clearly, as the dl element is in equilibrium, the force in the t cap direction is the same as the force in the minus t cap direction. So let's try to write that down. So at the start, we figured out that the tangent makes an angle theta with a horizontal, right? Now the horizontal is along this direction, right? So this angle is going to be theta. Similarly, even this angle is going to be theta. Okay, so the component of lambda dl ex in the minus t direction is going to be, so this is going to be lambda dl ex sine theta, and because of the ey component, it's going to be minus lambda dl ey cos theta. Okay, so basically this equation is just that we are balancing the forces in the t cap to the forces in the minus t cap direction. Okay, and once we do that, we get a scalar equation. Okay, and now we can just integrate this equation from the beginning to the end, and we'll get some interesting results. Okay, so now before we do that, there is another simplification that we can make here. So if I take lambda ex outside, the inner term becomes dl sine theta, and similarly on the other term, it becomes dl cos theta. Okay, so now if we try to draw the triangle, this was our dl element. We can break it down as dy. So dy will be horizontal because the y-axis is towards the right in this case, right? And then we have dx, and we have dx along the x direction. And at the start, we said that this angle was theta. Now from this triangle, we can see that dl multiplied by sine theta will give you dx, right? So this is just going to be lambda ex times dx, and the second term is just going to be lambda ey times dy. So now let's move this thing aside. So now what I'm going to do is I'm going to integrate this expression. The ex and ey is just a constant, so we can take it out. Okay, so we are starting from the origin, which is at 0, 0. The value of x and y are both 0, but the tension at this location is equal to mg. right? So the tension at this point is equal to mg. And coming to the older picture, this is our y-axis and this is our x-axis, and our final location is this point over here, which is at a y coordinate of s and an x coordinate of h, right? So our final y limit will be s and the final x limit will be capital H, and the tension at this location is going to be T. Okay, so the final tension is equal to T. The x coordinate is equal to capital H at the last point, and the y coordinate is equal to S. So now we can just integrate this expression. Okay, and once we integrate, we get this. So we get this particular equation, which, okay, so let's bring back the older equations. So these are the other equations that we figured out initially. From these equations, we can see that Ey is just mg divided by lambda L. So in the third, so let's say this is equation 3. So let's substitute everything into equation 3. T is equal to lambda L multiplied by Ex, and this is equal to mg plus lambda capital H Ex minus lambda S times Ey, which is equal to mg divided by lambda L. So from here we can solve for Ex. Okay, so and after solving for a bit, we get this value for Ex and this value for Ey. Okay, now the resultant electric field magnitude will be the resultant due to Ex and Ey, which will be equal to this particular value. Okay, so this is the answer to this question. The thing is, guys, I made a slight error here. I took the lengths the other way around. Okay, so this was S and this was equal to H. So I mean, that's not a big deal. We can just switch S and H in the final expression. Okay, so now it's fine. So H and S will be switched in basically every other equation. Okay, so yeah, that's about it for this video, guys. If you have any doubts, you can comment down below. And that's it. Thanks for watching.